Well, again, good afternoon and welcome to the kickoff, the inaugural presentation in our Earth Month series. Every year during Earth Month, we host events. They're usually on Tuesdays, but we have a couple of extra ones coming in this time, and they always start at 2 o'clock Eastern in the afternoon, as we see that seems to fit an awful lot of different countries and different time zones. So, first thing we have to do, obviously, is to read our disclaimer. We are a public outreach and a consulting organization. We're dedicated to advocacy for the protection of water as the vital human ecological asset is, and we do this through the implementation and management of affordable, appropriate wastewater systems. Wastewater education is a national and an international education service provider, and we host and facilitate these events, usually free of charge. For that, later on, we will be thanking our sponsors. We are independent, we are impartial. We assist individuals and communities to discover the financial and the environmental advantages of implementing sustainable, integrated water infrastructures. Because quite simply, as our logo says, water is water, not waste. Our disclaimer here is that we host and make these publicly available, and these should not be construed as an endorsement or a paid advertising. We do accept and encourage sponsorships and underwriting because this enables us to provide these educational events, again, at no charge. We invite you to visit our website, learn about our current and our upcoming events. And also, I'm going to put into the chat window later the link to our YouTube of our annual report. We are committed to making these educational events available to those with hearing, sight, or other disabilities, and those for whom English is not their primary language. So once the event has been published to our YouTube channel, you can access the closed captioning and the translation services that you can enable there. And you see here, at this point, we're going to show a short video. Let me put this one away. And before I get started, actually, I think I'm going to show the video and then read a small comment about this. So here we go.
The 60s brought the flowering of conservation. It was propelled by many things: air and water pollution, sprawl and development, massive fish kills and endangered birds, the Cuyahoga River catching on fire, and oil spills off California and Cornwall. But the real consciousness changer was seeing Earth from space.
In 69 and 70, we started to get real photographs of the Earth from space that completely changed people's perspective on themselves and their role on the planet. They were stunning because you saw a green, blue, cloud-bedecked, living planet in the background with, in the foreground, a dead moon with nothing but craters. The life-death image all combined in one beautiful and compelling scene was what people, I think, began to realize, that we could be the moon. We could be as dead as the moon.
All the social and political ferment that was going on in this country was building up and building up and building up. And on Earth Day 1970, it was like water bursting through a dam.
Charge the people $1.50 just to see 'em. Don't it always seem to go? You don't know what you got till it's gone. They pay paradise, put up a parking lot.
But I think you have to start out looking at the big picture. The big picture is that we live on a finite planet with a limited capacity to sustain life.
If we do not save the environment, then whatever we do in civil rights or in a war against poverty will be of no meaning, because then we will have the equality of extinction.
Earth pollution is mind pollution.
20 million people came out for the first Earth Day, still the largest demonstration ever. It catalyzed the transition from conservation to a new environmental movement and the next big issue, pollution.
Okay, now I know that this has been 50 years since the first Earth Day, because when was the last time any of you saw a mimeograph machine? And the fact of somebody taking a sledgehammer to that beautiful old car kind of makes me cringe a little bit. But yeah, it really has been 50 years since that first Earth Day. And, you know, that quickly became not just a United States movement, but a worldwide one too. So how far have we really come? Are we still going forward, or is there a sense that maybe we're sliding backwards and we're losing all the gains that we've made? We may have conquered past threats, but have we seen new ones replace them? And usually, of course, these are of our own making. Our Earth Month series really chooses to focus on both the continuing and the emerging threats to our shared environment. But also, we like to take a more positive view, focusing on what will and is driving technology, conservation, and environmental protection. We may get discouraged, and often maybe we feel like we're drowning in the politics and the vested interests, but humanity has always had an amazing ability to fight back, to find a compromise, and lead through innovation and the sheer force of the human brain, which is still the most powerful computer ever created. So throughout April, we're asking you to come visit our the invited entrepreneurs, the committed professionals in the water and wastewater business. We all believe that science is not and never will be optional. It is and always will be the solution. And to get us away here, I'm just going to hide this one and show a quick video which I think will put it in perspective.
Modern life is built on access to affordable energy. At home, at school, at work, and just to get around. But it takes more than pumping oil, harvesting wind, or digging coal to provide energy. It takes water.
We may fret in the United States about running out of oil, but water lubricates the American economy just as oil does.
Water plays a role in everything we do, whether it's turning on the tap or flipping the switch.
The energy business itself is a huge consumer of water, and we need more energy, which means we need more water. So what you have is a finite supply, and then you have increasing demands.
As we've increased the amount of energy we produce and consume, as well as our need for increased agriculture, we now find ourselves trying to get more use out of the same drop of water.
To meet future demands, we'll have to rethink how we use water and where we get it. Across the nation, energy companies and local governments are already taking creative actions to conserve and reuse water.
And for this, we really do have to credit PBS, the Public Broadcasting Service. We're allowed under a license to show educational videos, clips, as long as it's not for profit or for marketing purposes. So you'll see there in the bottom screen here the license for this from the American Legacy series, PBS Learning Media. The book, A Fierce Green Fire, that was mentioned in the first one, is still available on Amazon. So I am going to, let me put this somewhere, and I will make sure that we put this into the chat window. Here is the credit for the second video you've seen, and it's from a series, again, from Prairie Broadcasting, which relates the direct relationship between water use and energy use and conservation. And that is why we were particularly grateful and pleased when Michael Dooley and Claire Dooley from Strathkelvin, agreed to be our presenters today. And at this point, Michael, I'm going to switch over to you. If you would turn your webcam on, please.
Good evening, everybody. Thank you very much for attending our talk today. You can see on the map there that we're actually located halfway between Edinburgh and Glasgow in Scotland, part of the United Kingdom. So we're very much looking forward to sharing some of our experiences. We want to make this an interactive discussion, and we'd love to get your comments and questions as the webinar proceeds. There will also be a few polls throughout the course of the event, so please respond if you can. If you need or want to have any more details from the presentation, just stick a comment in the chat box and we'll be more than happy to do that. Also, great to have Paul Banfield and Michael Goldblatt, who are going to help the presentation along with myself and Claire. So again, really looking forward to getting this moving. So we are going to go through some of the global challenges for activated sludge and wastewater in particular. And some of the figures that I'm going to present will be well known to many of you, but they are worth repeating as it shows both the scale of the opportunity and the global challenge. So there are many reports which states that aeration consumes 30 to 70% of the energy for wastewater treatment, which in itself consumes 2% of global electricity generation. So if we take the aeration energy as an average 50%, 1% of electricity generated and its associated carbon footprint is used for wastewater operation. And once again, there are many studies showing that on average efficiency increases of 40 to 50% can quite easily be achieved on many wastewater treatment plants. Not on all, obviously, because some of them run very efficiently. Lately, we've been finding that many operators are looking to anaerobic digestion to reduce the overall energy footprint of the treatment process. And while this is very laudable, the relative investment to reduce aeration energy through the optimization process is significantly lower. And if we combine energy optimization with resource recovery and energy generation, then the activated sludge can become a significant part of the earth-saving refinery process. So I've extracted a couple of slides from the International Water Association presentation on water and wastewater, some of which I think provide quite a lot of information and sharing on some of the global energy figures. So here we can see how the cost of operation of a wastewater treatment plant, both in terms of carbon footprint and its associated energy costs, can increase significantly from the first bar chart showing just a BOD consent limit to the one on the very right-hand side showing 2 milligrams per liter of nitrogen and 0.02 milligrams of phosphate. So our challenge is, can we achieve cleaner discharges at a reduced environmental cost or penalty? And our experience, and that of many others, is that yes, we can, but we're looking at applying innovative science, improving resilience, and looking at the best practices in our fields. So what exactly is an efficient plant? You can see our first poll has come up. So where do you think your facility operates on the efficiency scale? Now, if we look at the German benchmark, which was completed around about 2007, they were looking at the best wastewater treatment plants on average running at 1.5 kilowatt hours of energy per kilogram of BOD removed. Now what I've done is I've translated some of that into flow measurements based on standard population equivalents of 60 milligrams per litre BOD and 200 litres per person per day. So that translates into 0.45 kilowatt hours per cubic metre processed, and I've also converted that into US units, which I hope I've got my translation factors correctly. Clearly, the other end of the scale is where people are consuming more than 5 kilowatt hours per kilogram of BOD removed. Now, for some plants, there can be very specific reasons. You might have very high pumping costs. You might have very high temperatures coming in. So, we're not criticizing anybody here, but I think it's always useful to try and find out where on that scale you sit. Looking at some of the figures that I'll present later on, you'll see that probably about the best efficiency you could ever gain is in the range of 0.2 to 0.5 kilowatt hours per kilogram of BOD. And that's really the maximum efficiency that your aerators, fine bubble diffused aerators can run at. So if you could give us some of your comments on the poll about where your particular plant sits, that would be great, and we'll leave it up for the next couple of slides. Again, I really like this picture from the IWA presentation, and this was presented by Dr. Nolasco, and you'll find his contact details in the acknowledgements at the end. But we're asked many times when we start to speak to people about how much efficiency can actually be gained from an optimization process. And again, there are many variables, but we need to consider overall the holistic plant flows from the actual plant design, the compliance requirements that we're operating to, as well as the current asset condition. There's no point in reducing aeration energy costs if you subsequently have to desludge the aeration plant every few years, or if indeed you reduce the operating life of equipment such as the aeration blowers. And that's why we've developed a very specific process to look at how we go through this, and most of that I'll share with you shortly. The photograph here is quite interesting because for the first time it showed me the difference between a cleaned fine bubble diffused aerator and a foul system. And you think you can very clearly see on the right hand side that in the clean system the bubbles are much smaller, and therefore the oxygen transfer efficiency is going to be much higher than the larger bubbles which are seen on the left hand side. There are actually now many devices which have been developed by companies, including the Water Research Council here in the UK, which can actually give an online measurement of the size of the diffusion bubbles, which could give you an indication about how efficient or how foul your diffusers are. So when we want to start to take our basic steps towards efficiency of the process, doing simple things like cleaning the diffusers, maybe once every 2 years, maybe a little bit more frequently depending on your process, replacing those diffusers at their end of their efficient life, which is generally in the 8 to 10 year time period, as the materials of construction start to embrittle and you can't get the same flexibility in the systems. But let's get on to the basic things, like let's clean your sensors, let's calibrate the sensors, which can often be more important, and then looking at your set points. I once did a presentation in the UK where I was introduced by the coordinator saying that he wasn't too sure what value he was going to get from the conversation, because he knew that if he cleaned these DO sensors, he would get a 10% improvement in aeration efficiency. And basically, I couldn't agree more. But we have to look at why, if we know all of this, and it's pretty basic science, aren't we actually doing that at the moment? And obviously, we've got resource and time limitations in all the plants. But that's why we developed some of the systems that we did develop for self-calibration and self-cleaning of the systems. So I'm going to move on to the next slide. Again, from the same presentation, we can look at the standard aeration efficiency, and you can see that there are significant impacts of fouling on the fine bubble diffused systems. Obviously much less on the turbines and coarse bubble systems, but then they run at a much lower efficiency coming in. So you can see that the fouling of the diffusers can quite easily make a 30 to 40% reduction in the actual aeration transfer efficiency, with cleaning improving it back up to almost 90% of at new. So we come back to the original question: can we improve efficiency and continue to protect the earth from some of the carbon footprint impacts without affecting our ability to achieve compliance? And what I've shown you here on this graph is an actual example from an SBR system in Cookstown in Northern Ireland. Now this is probably quite an extreme example of the efficiencies that can be gained because there were some specific issues running that site. But you can see that we're actually making a 50% reduction in the total site energy cost by optimizing the aeration process. Now I could actually do a whole webinar on what we did for that site and how we achieved the savings, and I'm quite happy if somebody wants to put a question in the comments to send a technical presentation on that. But suffice it to say that we used the OUR from the ASP-Con system to determine when the aeration cycle was complete for each basin. Then we terminated the cycle at that point and forced the basins onto the settle and decant cycles. This not only reduced the aeration energy consumption, but it also increased the whole plant's hydraulic capacity and improved treatment plant compliance performance. So, just take the opportunity at the moment to introduce the ASP-Con system. While most of the next slides will use the data provided by this system, the most important issue here is how the technical measures developed and in the main OUR can give a step change in the data available. OUR is the oxygen uptake rate, which is the total load on the system. So what you will see in the picture on the left-hand side is you see two panels, one of which is the local control and display unit, which is what links the system into the PLC and SCADA systems. Beside that we have our automatic calibration unit for the ISE sensors, and down at the bottom we actually have all the measuring sensors which are installed. There are 8 measuring sensors which produce up to 20 measures of performance for the treatment system. Okay, so the system can measure at a very basic level the dissolved oxygen, ammonia, mixed liquor, pH or ORP, and temperature and nitrate in the process. So these are the ones that will be known to many of you, and many of you may already have these instruments installed in the process. We can also provide and automate some of the laboratory analysis from the process. So we can do an online settlement test, and we can do that essentially as frequently as we want to. We've got one of our clients doing a settlement test every 40 minutes because they have a specific requirement. And because we know the MLSS, we can convert that into the SVI measure. Once we get into the really advanced side of the process, we can measure the oxygen uptake rate, which is going to form the main basis of the rest of our presentation. We can look at toxicity. We can also look at what are the required DO set points for operating the plant, as well as the percentage nitrification in the system. And later we can get into some really advanced online influent analysis, which I'm not really going to go through in any detail today. You might be glad to hear. But all those measurements are available in the standard setup. Okay, so the oxygen uptake rate measure has been known almost since the invention of the activated sludge process over 100 years ago. However, despite many iterations of the technology and the development of a lot of online systems and laboratory systems, the measure is not particularly used. And this is our next poll coming through from this evening, which is what is your understanding of OUR and how can it be used to control your facility. So this slide here is showing actual OUR test which was run on the Veolia wastewater treatment plant in Scotland. This is the plant for which Paul Banfield is the technical manager, and he will be talking about the benefits of the system to them, and going through how he's going to use the OUR to control his process going forward. But basically the system takes a sample. This ASP-Con is located in the anoxic zone of the wastewater treatment plant. So initially the dissolved oxygen level is 0. We have an aerator in the plant, in the ASP-Con itself, so we can add oxygen into that sample even though it's in the anoxic zone. And once it reaches a target DO set point, which you can change, we stop the aeration, and then we measure the rate of oxygen consumption in the sample against a specific part of the rate of decline of oxygen, which you're seeing here. So from that we can tell the total biodegradable load on the process at the time. which will give us the actual oxygen requirement, and it can be used to calculate the toxicity and some of the other measures which we mentioned before. The key message here is that OUR is now a very resilient measure because it's based on dissolved oxygen sensing. If you can clean the unit properly and if you can calibrate it properly, the DO is a very, very reliable measure, and therefore the OUR is a very reliable measure. And this is an example of feed-forward feedback control that we can achieve using OUR. So this example is from last month from a site that we are working on in Holland. We've installed the feed-forward device in the selector zone, which is essentially the anoxic zone, and the outlet system is measured just where the material overflows from the aeration system into the final clarifier system. What's quite clear here is that you have a sudden and significant upturn in load at the inlet to the wastewater treatment works. And if you were to try and run this with a standard DO control system, the DO control system would find it very, very difficult to respond adequately to the sudden increase in load, and you would be running your blowers pretty much flat out to try and catch up. At the same extent, when the load drops off, it's almost equally as dramatic. So, sorry, we've just got our daughter coming into the room here. So you can see that the OUR drops off quite significantly, but we can use the feed-forward feedback OUR loading to control the system and make sure that we attain compliance while optimizing the energy consumption. So we spoke a lot about self-cleaning and the importance of keeping the sensors clean to get the most optimal efficiency. So one of the things that we did as part of the development of our processes, we made sure that we developed a self-cleaning capability. And you can see here a photograph of a system that had been in operation in Chester in UK for over 8 weeks before we took this picture. So essentially the sensors are very clean. The two rectangular shaped devices are dissolved oxygen sensors. The circular units below them are the ISE sensors for ammonia, nitrate, and pH. Again, we talked a lot about keeping the systems calibrated, and this is how we do automatic calibration of the ISE sensors. So we have 4 fluid injections, which is done automatically from the pumping system that I showed you in the original slide. And you can see that each injection is sort of delineated by the sudden spikes which are caused when the sensors go into the air. So the injections 3 and 4 are used for pH control. You can see we've got a high and low for pH and also for nitrate, while the first 2 fluid injections are used for low and high ammonia. The computer software calculates all the calibration curves. We actually use the activated sludge bacteria itself for the LDO, luminescence dissolved oxygen, set point calibrations. So the graph on the left is the low point calibration, which causes the phase shift for the luminescence system to go high, and the one on the right is for the low point. Sorry, for the high point, I beg your pardon. But the critical point here is that these measures are all done under computer control, so you can set the timing of this to happen whenever you like. Normally we do it about 2 o'clock in the morning when we know the load is in most cases going to be quite low. Also, the calibration being under computer control is advantageous because it takes away any potential human error in terminating the calibration too early. We're shortly going to get some other people to talk to you and not have you too bored listening to my voice, and we're also going to show you some videos. But before we get on to that, we'll just go through some of the options for control. And you can see here this system is actually set up with feed forward from the anoxic zone, feedback from the outlet near the aeration system, and then actual control from within the aeration tank itself. The ASP-Con systems can communicate to the plant control network via Modbus, Profibus, 4 to 20 milliamp solutions, and most standard communication protocols. We've also developed bespoke solutions which are commercially available for fuzzy logic applications and SBR solutions. So we can gain direct control of the treatment plant blowers, control valves and aeration systems, as well as recycling rates through the PLC system. So I'm now going to introduce you to Paul Banfield, who is the technical manager for Veolia in the UK. Paul has been a good customer of ours for many, many years, well in excess of 10 years. And he's prepared this presentation about his experiences of aeration treatment plant optimization as well as the ASP-Con system. So Paul, I'm just about to mute my speaker and I'll hand over to you.
Okay, good afternoon, good evening everybody. Thanks for the introduction there, Michael. Yeah, so as Michael says, I've just got a few slides just to run through covering our experiences and the use of the ASP-Con. I suppose as a bit of background, we operate and maintain the treatment plant at Newbridge on a long-term contract. We're actually halfway through a 30-year operating contract. It's a small medium plant. It's about 40,000 population equivalent, and it's on the outskirts of Edinburgh. As Michael mentioned, we've been working with Strathkelvin on a number of their other respirometry tools. We've used the Strattox for troubleshooting and the Bioscope for optimization activities. So a few years ago, we were quite pleased to have the opportunity to review and validate the ASP-Con in situ at Newbridge. It was considered quite valuable to us at the time because we were sort of having a review internally of what sort of the digital future of wastewater treatment could be, and certainly with regard to the plant at Newbridge. Newbridge was an ideal site as we were looking at reducing our blower size. We had quite an underloaded plant from the original design, so we combined the use of this ASP-Con respirometry to actually help with that sort of blower sizing as well. See how I slide on. Okay, so with regard to how it works, we wanted to keep it very simple. We didn't want to overcomplicate things. We already had quite a robust control system which was operating on DO. So what we did is we installed the ASP-Con and we allowed that to measure the OUR load and the ammonia load. And from that, it was able to derive, or it's able to derive, a set point required for the blowers. Now that set point is from a lookup table, and the lookup table is adjustable in the commissioning settings. So we've got full control over that. So once the ASP-Con's measured the load, it then tells our blower PLC a derived set point, and our existing control system will then control the blowers modulating to hit the desired set point. If there's any problems with communication or the ASP-Con fails in any way, the PLC just automatically reverts back to our existing set point. So it was a kind of opportunity to have, I suppose, a risk-free opportunity to deliver the minimum amount of air required, but without having any increase in risk to compliance. That was one of the sort of key aspects from an operational sign-off point of view. So just below at the bottom of the slide, you can see the different set points. We've got a high, a low, and a low. And the high would be triggered if we were seeing elevated OUR and ammonium. If it was just elevated OURs, we might trigger the high set point. And then if both we're seeing low levels of ammonia and BOD load, we'd go into the low setting. And finally, during night times when there's very minimum requirements, we would go to the new small blower at a minimum set point range. So one of the things that we had to discuss with operations is why we wanted a moving set point. And as I said, that was mainly about giving the minimum amount of air required at any particular time during the course of the day or the process operation. I've got a screenshot from quite an interesting period at Newbridge, where we've got kind of a number of examples of why we've gone for this moving target. So this first one is, you can see a spike of both the ammonium and the O2 oxygen uptake. So this has triggered the high set point, where our blowers would be providing sort of max amount of oxygen. Now, typically we would have these spikes at periods now and again, and we would have to run our blowers at a reasonably high level to account for these and to buffer these spikes into the treatment process. But as you can see, it's a very kind of a small duration, so the ASP-Con is allowed to control the high set point to allow to blow up to the blowers to respond, but also then to ramp back down quite quickly when the load has passed through. There's a second example here where we've got the very low periods during sort of the very early parts of the morning, where we're seeing very low OUR and very low ammonia, and this is the time when we've set it up to kick into our small blower, just to really keep a minimum amount of oxygen provided to the system. And the last one is interesting because this is a spike not far off the level of spike in OUR we were seeing in the first one. However, there's no accompanying spike for ammonia on this, so this would only give our high set point. So again, we're responding to, I suppose, to two measurements to help maximise the efficiency of the system control. So if we have a look at sort of what this means in terms of savings for the plant. We've got two blower curves here. Apologies if you can't see this too clearly, but it's really two blower curves showing energy on the left-hand side versus airflow. The bottom one is for our small blower, and the one at the top is for our large blower. And as we can see, the vertical dotted line is where we're currently operating on an average airflow. So we've got our single blower sort of 3/4 up to what its maximum output is. Now, if we can reduce the amount of airflow required, just so we use the blower more in its midpoint, we can deliver about £10,000 worth of savings, about 12 kilowatt hours sort of operational consumption, which isn't huge amounts, but again, you know, it's the sort of aggregate of all these small sort of gains around which can add some big value. But the big value really for us is if we can step down onto the small blower, which is the curve at the bottom, and there's about a 35k saving, about 40 kilowatt hour consumption, but just by dropping onto that small blower. And we typically expect from looking at the data that we'll be able to run the small blower in its range to deliver the low, and the majority of the high situations. So we should really be seeing ourselves 80–85% of our operational time just utilising this small blower. And then with the final control, sort of ranging up and down the blower capacity, there's probably another inherent 12 kilowatts of saving. So overall, we're predicting about a 50k per year saving on what's quite a sort of a small to medium-sized plant. So I think that's taken me to the end of the slide. So thanks for listening, and again, my contact details, and you can drop a chat on there. So I'll hand back to Michael. I think he'll take us through another example.
Okay, thanks very much, Paul. I really appreciate you taking the time to put that together for us. So now I would like to go on and introduce Michael Gould to you from Solenis. Michael's a senior engineering consultant and professional engineer working in the water and wastewater industry. And we've been in contact with Michael for probably over 6 years now. First met him at WWTP in the USA. Michael's joined us on the telephone system today, so I will, without further ado, hand over to him.
Okay, can you hear me? Can you hear me? My phone is unmuted. Hello.
Michael, yes, we can hear you. Please go ahead.
Okay, thank you. I wasn't sure because I had trouble logging on here. So thank you, Michael. And let me start out by, do I have control of the slides here? Yes, I do. Okay. So let me start out by saying, yes, I had met Michael and his company at WWTP several years ago and was very impressed by what I saw in one of the early versions of the ASP-Con system and asked to learn more about it. Michael and his company introduced me to the first installation that they had in the USA and provided me with some data to look at that. So here is Milford, New Hampshire wastewater treatment facility. And here this one ASP-Con unit was set in the middle of one of the aeration basins, and I was able to extract some data and see what sense I could make out of it. Okay, so let's see. So here is a graph of 4 weeks worth of data. This is data that is taken down and put onto an Excel spreadsheet so that I could do some more analysis of it. And let me just say 2 things about this data, where we have average specific oxygen uptake rate data on the blue graph, and then the DO on the red graph. So if we look just above where it says 10, 10, 13, well, you can see that was 4.5 years ago. So just above there, where that first box is drawn, you can see the diurnal variations. Since this is a municipal system, you've got the diurnal variations where the oxygen uptake rate goes high and low in cycles daily on that. And as that happens, as the oxygen uptake rate goes high, we can see, and of course we expect, the dissolved oxygen to be lower in that system for a system that is not controlled by the loading. So we'll look at a better close-up of that one in 2 or 3 slides. But let us look at the trend. So in that first black square box there and the purple arrow, you can see that we have specific oxygen uptake rate that is averaging around 20 milligrams per gram hour. When we get to the 10, 17, 13 region, then that oxygen uptake rate has, on average, has gone up, and the dissolved oxygen in the system, in the aeration tank, is still going with the diurnal variation, but has gone down to 0 in some cases. So we're up over 5 milligrams per liter and then down to 0. So this of course lends itself to the next step of being able to control that, which both Michael and Paul have demonstrated in their examples. Now this is a very busy graph, but it has the same data as the last graph, with the blue being the oxygen uptake rate, the red being the dissolved oxygen, and then all the other things that were available on that unit 4.5 years ago. So we did get some mixed liquor solids numbers, with the axis on the right being the one that the mixed liquor solids goes with, and that turned out to be fairly accurate with what the plant was seeing as far as mixed liquor solids go. Some of the scatter here was unaveraged specific oxygen uptake rate, but once we did a 12-point moving average, we got those curves that seem to go along with the dissolved oxygen curves. So all this is very good information and very interesting. And at that point, that's what it was to me. Interesting, but that was a test where we got the data, but we didn't see any control on that yet. Okay. So back to, just to blow up part of that curve, where let's say we're at the second box here with the dissolved oxygen and the increasing specific oxygen uptake rate. So we have that right here, and here you can see where each box being 24 hours, you can see the diurnal variation. As the specific oxygen uptake rate got high, we got down to 0 on the dissolved oxygen. So what is that doing? Maybe that's causing some problem with filamentous, with low DO filamentous bacteria, for instance. So oftentimes what I see when I troubleshoot wastewater systems is at the end of the aeration basin is where the dissolved oxygen is measured. So, okay, our dissolved oxygen is 2 parts per million. That's fine. But what's really going on is what was able to be shown here on this ASP-Con unit, showing the instantaneous, very low dissolved oxygen in the middle of the basin. Now, this little drawing on the left is just a suggestion. Maybe if they're getting such a low dissolved oxygen, in this case, perhaps doing a step feed would be one possible way to mitigate that low dissolved oxygen. But of course, what was just demonstrated in the earlier examples of going high or low on the blowers is another way to mitigate that. That would be a perfect case for that. Now, I am usually in the industrial area. So what I was looking at was let me go to the next slide here. What I was looking at was a chemical plant in the Midwest. And besides the optimization of aeration, one of the things that I see often is a slug of toxic wastewater going to the aeration basin. Now, if we can identify that slug of toxic wastewater going to the aeration basin without waiting 24 hours for the operator the next morning to grab a sample and do the oxygen uptake rate test on it, maybe we can save some of these bacteria that oftentimes will be very compromised in the case of industrial toxic slugs. So in this case, we took just a bypass. The aeration basin was not in a convenient place to take the ASP-Con unit, but we could take a small bypass stream, and the operators at the plant put this barrel together where we took the bypass stream and put the ASP-Con unit into that, and we got some good data from that. So here's an example of some of the data that we saw. And in this case, the DO is red. Again, Here our temperature is, this is in Celsius. Even though I'm in the USA, I'm using Celsius here. So here we're at 40 degrees Celsius. This is in the warm part of the year in the Midwest USA. As it goes up, as the temperature goes up, we're seeing the dissolved oxygen, which is on the right axis, go down. Now, what's the cause for that? We didn't have all the information on that at the time, but this is one of the things, this is one of the trends that we can see, and maybe in Paul's system we go from a high to a high, in this case on the blower, because our temperature is high enough that we're not maintaining, we're not retaining enough aeration in the system. That should be about, yeah, let's see. Yes, that's all I have, Mike. And I do see this as a very promising technology. I'm anxious to try it again at some point soon. The energy savings, definitely, I see that part of it. But in my world of industrial wastewater, the early indication of a toxic feed water is really the benefit that I was looking for at first. So both of those benefits, energy savings and early indication of toxicity. Thank you, Mike.
Okay, thanks, Michael. That's fantastic. Thanks to both Paul and Michael. The guys have presented quite a significant amount of data, so we're going to do a little bit of light relief and show you a video that Claire, our marketing director, has prepared. So Dendra, if you wouldn't mind showing us the trailer video, and I hope you enjoy it. It's not very long.
I did post that video to our LinkedIn feed this morning, and it just goes to show, as I said, that we're in a really serious business and we do take this seriously, but there's no reason at all that we can't have a little fun. So thank you, Claire. Yep, go again, Michael.
Okay, can you hear me now?
Yes, I can. Thank you.
Okay, good. Okay, so apologies for that. Just start again. So the next set of case studies I want to present were from a company, SPEN, in South Korea. You can see a picture there of the SPEN management team, as well as the people from the SONIM wastewater treatment plant where we installed the first system I'm actually just back from South Korea yesterday, so I'm still more than a little bit jet lagged. So I promise to try not to fall asleep, but obviously doing the presentation is helping significantly with that. So SPEN are South Korea's foremost distributor. I should point out that because it's 3 a.m. in the morning over there, I'm presenting their slides for them. We do have Jamie Lee, who's heavily involved in the rollout and the initial setup of the ASP-Con for South Korea on our webinar today, and if I say anything incorrect, then I'm sure Jamie will type up in the chat box. For many years, OUR has been recognized within South Korea as being one of the key technologies that they can use to optimize their wastewater treatment process. However, the equipment hasn't been available in the market to reliably produce the results. We did the first installation with the team over there 9 months ago on the SONIM wastewater treatment plant, and I'm going to show you a little bit more detail of that. The picture on the left-hand side are two of the people from SPEN at an installation on the CJ food producing plant, which is what we were working on last week, and actually physically connecting it to the PLC system via some 4 to 20 milliamp loops there. The important point is this team have worked really well and have been very impressive at taking on the installation, the operation and the management of the systems, as well as introducing it to the market. And they have now completed trials with 3 different companies over there, so CJ, the Namhang industrial area, and the SONIM wastewater treatment plant. And all of those have resulted in a successful conclusion of the approval of the technology. So specifically on the SONIM plant, which is the largest wastewater treatment plant facility in the region, when we went to install it, we were made very welcome by the owners of the plant, but they told us that the plant was significantly overloaded due to significant local area population increases and industrial discharges. And while they were more than happy to review the technology, they felt that they wouldn't be able to do energy optimization on the plant. In actual fact, as you can see from the graph on the left-hand side, while the plant is probably massively overloaded at certain points in time, there are also significant time periods when the plant is quite underloaded. And at those points we can see the dissolved oxygen rising just exactly as you've seen from both Paul and Michael's presentations. So we could find out that if we did actually do feed-forward loading, that the energy consumption on the plant could actually be optimized. And this week past, I was discussing with their control and automation engineers exactly how that could be achieved, and I think they're quite excited by the possibilities. So apart from saying that I really appreciate the time and effort from the SPEN people, I'm going to move on to some other case study examples. So, looking at how the ASP-Con system can be used for advanced real-time control, I'm quite conscious here that this is potentially starting to sound like a sales presentation, and I really don't intend it to be, because there are different ways in which you can make some of these measurements using different manufacturers' instrumentation. So I'm really just trying to present how the technology can be used to optimize the process, and I'm just using obviously data from our own system. So, okay, we were going to at this stage do a video showing you the actual physical components that Claire had put together, but I think...
Hi, we all know seeing is believing, but unfortunately we can't physically take you on a site visit today, but we are hoping, if the video works, we've put together a short video tour of an ASP-Con installation in Glasgow in Scotland. We're hoping to show you the main components of the system, how they're placed on the railings, etc., how the system is actually cleaning itself, so our ASP-Con can keep the sensors really clean during its operation lifetime. Never mind the technical issues we're having, we did have some dubbing issues on this video, because after shooting it, we couldn't edit the horrendous noise that was going on in the background. So in the last clip, if we're managing to show it, you will be able to hear the horrendous noise when we show the sample that we exhaust. So we'll give the video a try. I'll pass you over to my...
Hi, I'm now going to show you how easy it is to lift the ASP-Con out of the system for maintenance
Right, that's
purposes.
Claire actually standing beside
You don't need
the
your
manual
porridge.
winch. So, Dendra, if you could actually pull that video and we'll go back to the slides. There we go. Perfect. Okay, so appreciate everyone's patience. I know we're getting towards the end of an hour here, so we will just go through the last couple of slides here and then maybe get some feedback on it. So this is one of the wastewater treatment plants where about a day or two after we completed the installation, we detected a plant upset condition. Actual fact, we discovered this on a Saturday morning logging on via the remote access on the plant. And first of all, we saw the ammonia starting to rise significantly above what we expected. So we immediately pulled up the OUR data, and that confirmed absolutely that there was a real incident on the plant. It turned out it was associated with a failure of the air supply line to the plant. But the real important point here is that actually knowing that the DO had flatlined, that the OUR had gone up, and the ammonia had gone up, gave us absolute confidence to be able to report to the operations team that they were suffering from an incident. Again, very similarly, you'll see this was New Year's Day, just gone by, 3:10 in the afternoon. One of our other clients on a landfill leachate site had a significant spike in OUR on the outlet of the process. We can see the coincidental drop-off in dissolved oxygen, again confirming that there was an upset condition going on. But in this case, similar to Paul's, we didn't detect any ammonia in the outlet. So really a strong indication that if you want to get the ultimate level of plant control, you need to measure OUR as well as measuring ammonia. This is the same site, it's actually the same period of time, and we actually are lead consultants on this plant and have been for many, many years. And one of the operational issues that we have struggled with the client for many, many years is some challenges on suspended solids in the outlet. It's never out with compliance, but it's quite variable and something we would like with the client to get significantly better control on. Before we put in the ASP-Con, the site operator was carrying out 1 and sometimes 2 settlement tests per day. But the reality is that the majority of the time these settlement tests were coming back around about 90% settlement. So it didn't look like the solids issues were being caused by poor settlement. But once we automated the process and we started to take the samples and run them every 6 hours, we can see that there are frequent time periods when the settlement is actually very poor, because bearing in mind this system is installed right at the outlet, it's going to mimic the performance of the clarifiers, and you can see that sometimes it's as low as 20% in the system. So this is just investigative data. We've not come to the conclusions as to why this is happening yet. There are many varied reasons. This is something that Michael mentioned in his presentation as well, is the ASP-Con is an excellent source of information. How you design the systems and then run forward will depend on what you want to achieve. But the most important starting point is to have accurate and reliable data. This is actually the plant that Michael spoke to you about at Milford, New Haven, and this goes back to quite early on in the development phase of the ASP-Con system. It was a little bit later than the data that Michael had gathered, and we'd actually made some improvements to the system based on some of his findings and some findings from the site. What you can see here is the control available when the dissolved oxygen and ammonia are combined together, and you can see an absolute matching of the dissolved oxygen and the ammonia spikes. What you can also see here is that in between the ammonia spikes, they're running the dissolved oxygen very high, greater than 2.5 milligrams per liter. So if we can get control of the plant whereby we can be confident about being able to detect the increase in load before it happens, so that's in the anoxic zone and where the Asprin controller is itself, during the low periods we can actually drop down the dissolved oxygen level and gain some significant energy savings. So you will be pleased to note that that is my last slide, and what we would like to do is pull up the last poll, Dendra, which is the question on OUR and respirometry and where we are. I'd like to thank people who have acknowledged, who have contributed to the presentation today. So the first 4 people are the people who prepared all the materials for the IWA presentation and generously gave me permission to use their data and present it as part of this, which I really appreciate. Then you have Daniel and Alaska, who actually did that presentation, Paul Banfield and Michael Goldblatt, who both did sterling work in presenting those presentations. Claire, who you just heard from briefly in the presentation, unfortunately, it would have been nice to see her whole video, but hopefully you'll see that on YouTube. And our business colleague and co-owner, Martin Burns from Strathkelvin, who did a lot of the engineering development work and the electronics and software on the ASP-Con system as well. And last but not least, Dendra, who has been working with myself and Claire now for several weeks and months and giving us advice and you know, allowed us to make our mistakes and educated us on the best way to do it. So hopefully the next presentation will be even better. And lastly but not least, thank you all for joining in and listening and sticking with us. We really appreciate it. Has anybody got any questions? They can either put them into the chat box or...
Yeah, and actually we do have a flash version of Claire's video. So at the risk of it not playing again, let's give it a try, shall we? Sometimes this works better.
Hi, so we have 3 pieces of equipment. This is the control panel, the calibration unit, and behind just over there, that we will show you in a minute, is the actual ASP-Con sensor. Within the control panel, we have it all set up to look at all the different parameters we are actually measuring in the wastewater treatment plant. The operator has a specific screen that he can look at to see what is exactly going on in the plant right now. He can also look at the screen from the security of his computer in the office, but as you can see, we're out on a sunny day in Scotland. The thing is, in all weathers, hail, snow, and in America, I know it's probably scorching sunshine. You can check here or in the office. This is our local control panel. It gets all the information from the sensors in the ASP-Con and gathers it all together and does a lot of the calculations, and has a screen that the operator can see and what's happening in the plant here and now. Hi, I'm now going to show you how easy it is to lift the ASP-Con local plant here and now. Hi, I'm now going to show you how easy it is to lift the ASP-Con out of the system for maintenance purposes. You don't need your porridge, I haven't had mine this morning, or your oatmeal. This is how you do it. This is a manual hoist. We also have an automatic hoist on the system. In this system we have the puck with 4 sensors, ammonia, pH, nitrate, as well as a reference, and we can also swap for an ORP, which was asked of us at WWTP a number of years ago, which we introduced to our ASP-Con for our American clients. As easy as that. And there are the 4 sensors, all nice and clean. As you can see here, this is the internal LDO. This measures the oxygen uptake rate for the test from the grab sample. This is the custom-made aeration stone, and we also have a rotor which ensures the sample stays in suspension throughout the whole process. We have the external LDO, which measures the oxygen within the plant the whole time while we're running all the different tests, and the different sensors here gather the rest of the information we require.
And there you go. And what I can do as well, when we get into your closing screen here, I'll upload those videos so that people can download them and share and watch to their heart's content. So at this point, let's see here, you do have a couple of people in your poll here. Let's move on to the final screen. And here is some contact information for Michael. If we have contact information for Paul and for the other Michael, we can pop that in there. I will go ahead and preload into the file sharing pod here those two videos so that people can download. You can download the whole thing as a zip file, or you can select and download individual ones. Are there any questions? Does anybody would like a microphone? If they do, let us know in the chat window. We're happy to turn one on for you. And while people are thinking about that, Michael, there are a couple of questions that came in via text. And just to remind people that I think we mentioned that in the invitation, that there was the ability, if you wanted to send a text in. What is the minimum plant size that the ASP-Con is appropriate for?
Okay, so initially when we were designing this system, we started to design it with large wastewater treatment plants in mind, where they would be using multiple units. What we're actually finding now is that that is still a key market for us, but also unmanned smaller wastewater treatment plants where the overall management team can decide when people will visit site, and if they have problems on the site, is actually becoming a significant market for us as well. The payback scenarios are really in terms of compliance, energy optimization, and reducing operator workload. So obviously on the smaller plants, energy optimization won't be such a big factor, but the compliance and operator workload ones can be. So we are looking at some clients who are looking at quite small wastewater treatment plants, maybe about 5,000 population equivalent, or even smaller. Initially when we designed, we were looking at potentially around about 20,000 population equivalent. So I hope that answers that question.
Okay, thank you.
Yeah. And just Claire's reminded me that one of the things that we're working with here locally in Scotland is plant flow and load surveys as a portable unit for sizing aeration systems, but also for sizing the actual physical size of the plant itself.
A question via text. How do you determine what is the level of OUR, which is the endogenous or treatment complete rate?
Okay, so this is on the feedback control. I think actually there's a photograph that I put into the Dropbox, might be called cyclical respirometry on that, Dendra.
And apologies, this is going to overlay the contact information, but we will put it back here momentarily. Yeah, so there we go. How's that?
Okay. Okay. It's come in slightly blurred, so apologies for that. But what we can do is we can run a specific test using the ASP-Con itself. This is an example from our Glasgow installation. And what we do is we do cyclical respirometry on a retained sample. So normally when we do the OUR test, we discharge the sample back into the system immediately. But in this example here, we can continue to treat it within the ASP-Con system itself. And that draws the OUR curve, which would be from fully loaded, about 40 milligrams per liter per hour on the y-axis that you can see here, down to little over 20 milligrams per liter per hour after 4.5 to 5 hours treatment. So the last measurement, 22 milligrams per liter per hour, is the endogenous or fully treated respiration rate. So we can either do that as a specific test, or indeed, when we normally install the systems, we would run them for about 6 to 8 weeks to gather some baseline data, and we would be able to determine whether the OUR at that endogenous level is correct.
Several people who have registered for this event from fairly remote locations, and one of them sent a question in ahead of time. As we are not that well connected to the power grid and it fluctuates fairly frequently. Is there the ability to run the system using alternative energy sources such as photovoltaic, battery, wind power, solar power?
Okay, so the actual energy requirement for the ASP-Con itself is fairly low. So our maximum energy consumption is 10 amps. We normally have either a 240 volt or a 110 volt supply coming into the system. But there's absolutely no reason why we can't run on DC current only. So while we haven't actually connected it up to solar or battery facilities, there's no technical reason why we can't do that.
Chat window here, Michael, from Raphael. Is any training program available for the ASP-Con unit? Online if possible.
Okay, so we have a fairly comprehensive, in fact, a very comprehensive training manual available on PowerPoint, which we would be happy to pass on to people and allow them to see that and have the information on it. We also, obviously being a CE compliant product, we have full technical and operational manuals on it. One of the big advantages, in fact, we probably couldn't have commissioned this system and made it operational without the remote access capability for the system. So as standard, each ASP-Con itself is provided with a router, and the customer can put a SIM card into that, and we can access the system and go through any fault diagnosis or training with them on the system. In fact, at the moment, we are supporting the people in South Korea when they need it. On one occasion at 2 a.m. in the morning when a specific problem popped up. So yeah, there's quite significant training resources available, but also we've learned a lot, especially the people in South Korea, about the requirements for supporting in remote areas, and that's really worked very well. We have FaceTime with people on systems as well to work it through.
Okay, I do see another.
So I see there's another question in from Raphael.
No, I was agreeing with you.
Sorry, Dendra, go ahead. All right, okay. So actual fact, this is something I was discussing with Paul earlier on today about in-sewer sensing and what we can do on that. So the system can be integrated with other sensors, absolutely. We would normally do that via PLC system and control, but in actual fact you can install the ASP-Con unit itself in the sewer, in the river applications. Up until now, we have been able to do all the measurements that don't require the bacteria, so essentially we couldn't do the OUR. But the conversation I was having with Paul today was about how we could potentially do the OUR within the sewer and do a toxicity test, and I think I've cracked the technical solution to that, so we will be probably presenting that to people in the next few days.
Any other questions, ladies and gentlemen? As they say, speak now or forever hold your activated sludge. Not seeing any. Michael, I'm just going to make your video a little bit smaller here. And remember, there is a closing poll here. If you would like more information, do go ahead and enter that into this. And at this point, Michael, I'm going to ask you to stop your video feed, please. And
no problem.
No,
I'm sure people are sick of seeing me.
Let me just move that out of the way here. We do have a couple of closing items that we need to cover. First of all, obviously, we do need to say thank you to our underwriters. So let me move these over here. Again, although we do not provide materials for for direct advertising. We couldn't do this. We are a registered nonprofit, 501c3. We could not provide these education events without the support of our generous sponsors. So obviously we want to say thank you to Parson Environmental and to Conceal Concrete Sealants. And we've done a couple of events for Parson dealing with I&I and with rehabilitation. And we've also done one in the past, and we're about to redo another one with Conceal about microbial concrete corrosion. Let me put this one away. The other activity that we do during Earth Month is obviously we talk a lot about people who are really not in at all a position to be involved with some of the technology and the advances that we enjoy the luxury of here. So during Earth Month this year we are advocating for two other nonprofits. Obviously we'd like to advocate for ourselves, but that seems a bit self-serving to us, and during Earth Month we are advocating for water.org. Let me put that address into the chat window. You may have seen the campaign Buy a Lady a Drink. They have partnered with Stella Artois. You can purchase a chalice through their directly from water.org or from Amazon through our Amazon Smile program. If you purchase one of these chalices, which I did and we gave a bunch of them away for our speakers before, you are in effect providing clean water for 5 years to someone who at the moment is spending the majority of their life just carrying and fetching clean drinking water. Just think about that the next time, maybe if you watch one of the YouTube videos from water.org. How would you like to spend your entire day walking for miles and carrying a whole ton of water back on top of your head or by a yoke across your shoulder? This is no way to live a life. And of course, if you're in that kind of existence, you have no time for education, you have no time for advancing your own economic well-being. The other organization we are advocating strongly for at the moment is flintkids.org, and I'm putting this into the website, into the chat window. The Flint Community Foundation, some of you may know about what happened in Flint, Michigan with the widespread lead contamination of the drinking water system. Some of you may not. If you go to flintkids.org, you will find out what the end result is, that far too many children will be living with the effects of severe lead poisoning for the rest of their lives, and their medical bills are going to be astronomical. And so the Flint Community Foundation there have established a fund specifically to channel funds for those purposes. We would very much like to thank Michael and Claire and Michael and Paul and Jamie Lee for contributing to this event today. It's just the first, it's just one piece of the puzzle as far as where is our water coming from and where is it going, and will there be enough there for our children and our grandchildren. Obviously we hope there will be, and we look to people like Michael and all the other people who have agreed to be presenters for us during Earth Month to make that happen. And at this point, we're going to close out of today's event by hopefully not buffering a short video again from Prairie Broadcasting about exactly what we're talking about. If this does buffer, don't worry, I will put it into the file download window for you. And again, this is shown courtesy of Public Broadcasting Service.
The city of Los Angeles has struggled to meet demand for more than a century, going farther and farther afield to get water for its ever-growing population. Today, reuse and conservation are helping the city make better use of the water it already has.
The Department of Water and Power serves the entire population of the city of Los Angeles, just over 4 million people. LA gets its water from 4 primary sources. Over 85% is imported. That's from 3 sources, from the Colorado River, from the Eastern Sierra, and from the western side of the Sierras to the Bay Delta area. The remaining water is groundwater from the city of LA.
Years ago, the city tapped the last available sources of fresh water. Now, Los Angeles is starting to squeeze more use from the water it has. Instead of discharging millions of gallons of treated wastewater to the ocean, Los Angeles is recycling it for new uses.
We take the tertiary treated water from one of the Bureau of Sanitation wastewater treatment plants, and we then pump it for irrigation or the industrial uses such as cooling towers. We currently recycle just over 1% of the water used in the city of LA.
Conservation and recycling have held the line on water use.
Even though LA increased in population by over 1 million people, we still use the same amount of water that we did as of about 20 years ago.
Which is quite a staggering thought, that you really can recycle wastewater. In fact, everybody that drank coffee this morning and then went to the bathroom afterwards is already recycling wastewater. And in fact, the next event in our Tuesday at 2 Earth Month series is called The Awful Truth About Poo. The amazing things that you thought you knew, and hopefully after this event you realize that you knew absolutely nothing at all. At this point, Michael, Claire, if you would like to sign off and let everyone know how they can contact you or any other comments. If anyone has any other comments, feel free to go ahead now.
Okay, everybody, thank you very much. I appreciate your time today. We're just going to put our email addresses into the chat box. So thank you once again, and look forward to speaking to you all or being attendees at one of these presentations that are coming up.
Yep, thank you. The other two that are scheduled later this month, and I put the link into the chat box for our Tuesday at 2 website. We have a presentation about the going back in history to look at where all this started with the Leonardo da Vinci water engineering studies. And also we're going to do a review of the water infrastructure repairs progress of as a result of Hurricane Maria and Hurricane Irma that decimated the Caribbean, not just Puerto Rico, but the Lesser Antilles and the U.S. Virgin Islands. So at this point, ladies and gentlemen, we are going to stop the recording and wish you a wonderful rest of your day, but we will stick around in case there are any other questions.